Hello students, today we are just going to discuss jury stability test. This test is applicable in case of jet transformation. That means when the signal is available into the form of pulses, then this test may be applied to check the stability of the system. Now, first of all, introduction. For continuous time system, the Routh-Hurwitz criteria offers a simple and convenient technique for determining the stability of low order system. This part you had already seen in case of linear control system, that means in case of LCS. Now, since the stability boundary in the Z plane is different from that in S plane, the Routh-Hurwitz criteria cannot be directly applied to discrete time system if the system characteristic equation is expressed as a function of Z. That means when the equation is into the form of S plane, we are simply capable to apply that Routh-Hurwitz technique, but when that characteristic equation is given into the form of Z transformation, we are not able to apply that Routh-Hurwitz criteria directly. Then after that, a stability criterion for discrete time system that is similar to the Routh-Hurwitz criteria and can be applied to the characteristic equation written as a function of Z. As we had already discussed, Routh-Hurwitz criteria is applicable in S plane when the characteristic equation is given into the form of S plane. Similarly, this jury stability test is applicable when that characteristic equation is given into the form of Z plane, given as a function of Z, right? Then that means we may conclude that jury test is used directly on the characteristic equation which is in Z transform. If the equation is into the form of S transform, then we may apply either pole zero diagram or that Routh-Hurwitz criteria. And if the equation is given into the form of Z transformation, then this jury stability test is the best applicable method to check out the stability of the system. Now, let us say how that procedure is applicable in case of that jury stability test. Before starting, let us take the equation as this equation. This is the equation an z base to power n plus an minus 1. Let us say this is the characteristic equation. Now in this case, you may simply see that here z base to power naught is inserted, right? That means coefficient of z base to power naught is a0, coefficient of z is a1, coefficient of z square is a2, and so on, and at the end that coefficient of z base to power n, that is given as an, right? This is the characteristic equation which may be given to you in any case, in any numerical, and from this characteristic equation you will have to make this Routh-Hurwitz table. This is the Routh-Hurwitz table. In this case, if you will see, in the first row all the power of z are simply written, z0, z1, z2, and so on, right? And here this first row represent coefficient of corresponding power of z, a0, a1, a2, an minus 1, right? And similarly here that last, these all are the coefficient of this characteristic equation which will be given by this equation number 7.13. Fine. Now second row of this jury table, that may be simply invert of that first row. In first row here it will be an minus 1, and so on like that, and first element is a0. If you see that second row, in second row the elements will be, first element will be an, which is the last element of the first row. Similarly second here, that will be an minus 1, here it will be an minus 1, and here somewhere it will be an minus 2, so third element will be an minus 2. And if you see that first row, here it will be a naught, and in case of the second row, last element is a naught. So first and second rows of this jury table that are just invert of each other. Then after that we will have to calculate this b0, b1, b2 and so on up to bn minus 1. And this is your third row that we will see in the next slide how to calculate that b0, b1 or so on. And but if you see that fourth row is again invert of the third row. By using the first and second row, you may calculate the third row, and fourth row is invert of the third row. You may see here last element is bn minus 1, and here first element is bn minus 1. Then here it will be bn minus 2, and here it will be bn minus 2. First element of the third row is b0, and last element of the fourth row is b0. Now by using third and fourth row, you may be able to calculate fifth row, and invert of the fifth, that will be just sixth row. This process is continue till we are getting only 3 elements in the last row. We are not going to proceed whenever we are getting only 3 elements in the last row. And if you see in each of the odd row, 1 element is going to be decreased. In the first element there are n number of the elements, in the third there are n minus 1, in the fifth there are n minus 2 and so on. This process will be continued, and at the last row you will get only 3 elements. At that point your table is just going to be finalized. Now after that, from this table what we will have to check, right? Now see, this is your characteristic equation. From this characteristic equation you have just made that jury table, right? Now see here, this is the value of bk. Bk is equal to a naught first, and then an minus k, an, ak. Bk, k may be 0, 1, 2 like that, right? And this will be simply a naught into ak minus ak an into an minus k, right? You may substitute any of the value of k and calculate the values of the third row, right? Similarly for the fifth row, you will get b naught from the rows third and fourth. You may calculate that fifth row. This will be again simply b naught into bk minus bnk into bn minus 1k. And similarly from fifth and sixth row, you may calculate dk, right? These are the elements of the fifth and sixth row, right? And by using these elements, you may calculate that d, that means elements of the seventh row. Now what to check from these values, what we will have to check, and how you are able to comment whether the system is stable or not. Now simply, this is your equation, this is the characteristic equation, fine. Now in this case, what is first condition to check? First condition is q1, that means instead of z, substitute 1 here, right? And if by substituting 1 your value will be positive, right, then your first condition satisfied. Then we will proceed towards the second condition. First condition is q of 1 must be greater than 0. So q of 1 must be greater than 0 means here substitute in place of z, substitute z is equal to 1, and check out whether this equation will be greater than 0 or it will be negative. If it will be negative, then your first condition disqualify and we are not able to apply second condition. Now what is the second condition? Second condition is minus 1 base to power n q of minus 1, right? This must be greater than 0. So here simply substitute z as minus 1 and multiply that resultant with minus 1 base to power n, where n is the highest power of the z present in the characteristic equation. Then if these two conditions satisfy, then we will have to check the other condition. First condition is from the characteristic equation, a naught magnitude mod of the a naught Mod of the A0 means coefficient of z raised to power 0. This must be less than an, right? If this satisfy, then all other are in term of the greater than. B0 must be greater than Bn minus 1, where that elements are in this table, right? B0 must be greater than Bn minus 1, C0 must be greater than Cn minus 1, n minus 2, and so on. So if these conditions satisfy, then we may say that here, if these conditions satisfy from the table and from the characteristic equation, then we may be able to say that this jury stability test shows that this is the given equation is stable. The given equation represents the stable system. Now, after that, let us take one example based upon the same. This is the conclusion of all that. What we will have to check, we had already discussed in the previous slide. So here q of 1 must be greater than 0, minus 1 raised to power n, q of minus 1, that must be greater than 0. And second thing, a0 will be less than an. These are required, right? For this, we didn't require any calculation part. That means these may be calculated, check out from the characteristic equation only. And after that, just make the array or table, and from that table you may check out the remaining equation, right? So we are just going to apply this on this characteristic equation. Let us say here this is the characteristic equation. Qz is equal to z cube minus 1.8 z square plus 1.05 z minus 0.2 is equal to 0. So this is the characteristic equation. This is in term of closed loop discrete time system, and from this equation we will have to check whether this will describe a stable system or not by using the jury stability test. So first condition is substitute q is equal to 1, z is equal to 1, right? So if q1 is equal to, simply substitute in this. If you will substitute instead of z1, then you will get this will be 0.05, which will be greater than 0, right? Then second condition is minus 1 raised to power n, q of minus 1. So n is equal to 3 here. N is the highest power of the z. So here you will get, after substituting this, you will get this result. Then see this here. These are the elements from this characteristic equation, right? And this is the invert of the first row, 1 minus 1.8, and third row elements that may be calculated from this. First 0.2, 1, and second is last 1 minus 0.2. By using this minus 0.2 into minus 0.2 plus 0.4 minus 1, right? So this will be minus 0.96. Similarly, B1 is equal to, first row will remain as such, and second will be these elements, fine. Similarly, B2 will be these elements, first and second. So you may calculate these elements, and then after that apply remaining condition. So first is A0 mod will be less than An. This is applicable here. A0 is 0.2. This one, mod of the A0, and An is equal to 1. So that is less than. So first condition qualify. Then after that, second condition is this one. B0 will be greater than. This is also qualified. Mod we are taking the mod of that. And because all these conditions satisfy, so you may say that the system is stable. All the condition of the jury stability test has been satisfied, so the system is stable. Thank you.